Any questions before we begin?
Did you wake up?
What's that now?
Did you wake up this morning?
Yeah.
Very quick.
Yeah. I felt it. I felt it.
Just as I was going back.
What was that?
4:50.
Yeah.
I was woken up by it, but
First time I thought I was gonna die.
Okay, let's go ahead and begin, folks. Just a quick announcement, right? Next week, 7th week, yeah? What's going on next week? Something's going on. Oh, yeah. Thank you. Oh, I almost forgot. Yeah.
Did that get canceled?
Sorry.
So yeah, next Wednesday. Okay, same policy holds as last time. We can have a few more discussions about it tomorrow too, but I just want to make sure that you guys are all got your heads up. Closed book, closed note. You don't need paper. You don't need a calculator. You don't need anything but something to write with. Use your brain. All right.
Is that going to be up through lecture 9 or?
It will be up through everything that I cover through tomorrow lecture. Nothing on Monday, nothing on Tuesday of next week. Okay, so we'll cut it off there. And then, and potentially any homeworks that are relevant to those material as well that I will be most likely handing out tomorrow. Just want to make sure, I mean, you guys hold me in contract status with some of this stuff. Just in case I write something there. Okay, very good. So let's just briefly go back to where we were last time. Again, I was on this case study walking through the max data analysis. The purpose of me doing this case study is a couple of things. One is to give you kind of an idea of the types of descriptors that I would be doing, both on the EDA for the covariance side of things, but also I'm doing some kind of simplified, if you will, EDA to assess the scientific question of interest as well. And remember, that scientific question of interest is we're wondering whether the trajectory of individuals' CD4 counts differs depending upon what their baseline disease severity status is. And disease severity status here is measured by their baseline viral load counts. So what I had done last time, we've done quite a bit on the covariance structure. So I think the variogram kind of sums it up quite well in that you have lots of measurement error in this particular process. That's because you're sampling for viral load counts. You have this concept of heavy random intercepts, and that is that individuals tend to be high or low with respect to their CD4 counts just all the way through time. Okay, and you can see that pretty easily in the spaghetti plots that we had as well. So we were expecting that. And then when we look at the empirical covariance structures and correlation structures, we saw that there was some serial correlation that kind of dropped off as we went through time. Okay, and so that's kind of this slope that's coming up here, meeting this kind of plateauing sill, people call it, in the literature. Okay. So as you're thinking about choosing an appropriate weighting scheme, you might think of something autoregressive in nature, but wanting to have some sort of common correlation across any point in time in there as well. So one of the things that I had written down for you guys early on in class was kind of a hybrid variance covariance structure. This is kind of an example of that hybrid variance covariance structure where I had kind of a sigma 1 that was this exchangeable covariance matrix, and then I had an AR1 process on top of that. I hate to build you up and then let you down, but the fact is that's actually not implemented in R. It is implemented in SAS, it's not implemented in R. So we're going to kind of look at an exchangeable and an AR1 structure in just a minute here. But it wouldn't be that hard to program your own, actually. Maybe we'll do that for a homework assignment or something like that. So, you just obtain method of moments estimators for each of those individual components that go inside of the constant correlation and then the AR1 process. So, okay. So that's what we learned there. And then I investigated a little bit of This is preluding really lecture 9, where we're going to get more into a kind of a random effect type of structure, where we just build on, say, random slopes, for example, along with random intercepts. And so I looked at some visual plots that I will tend to use where I fit just individual level linear regression models, estimated each person's intercept just based upon their slope, on their individual data, estimated their slope. And again, the idea here is to look for variation across these things, and that's indicative then of random intercepts, and then of course random slopes on the other side. We saw quite a bit of variation when I showed you guys the full plot last time in the intercepts. Slopes, not quite as clearly, and you can see that here. There's a lot of overlap. Like if I draw a straight line down the middle here, most of these CIs are going to fall or cover that straight line, okay, as I'm going through. That's not the case sitting over here with the random intercepts, and certainly not when you look at all of the data. And then finally, I took that same kind of structure that I had where I had these individual level fits and said, well, maybe we can get some descriptors on the scientific question of interest. And so I did a few things. I said, look, if you want to know whether the trajectory is differing depending upon baseline viral load status, take each individual's estimated slope. That now becomes a univariate response. That takes you right back to where you were back in the 210 days. Okay, it's just independent data now, univariate response for each person. It's just their beta 1 hat, if you will. Okay, and so you could look at that and say, okay, now I've got this response, which is my individual level slope. I could look at, say, distributions of that across the different 6 categories that I created. And again, those are fairly arbitrary categories. I just cut the range of log baseline viral load into 6 parts. And what we saw there was there seems to be an impact going on among people that have very, very high baseline viral loads. In other words, our highest group in these individuals, but the other slopes tend to be pretty consistent there. I also then said, well, maybe we could do something a little bit better in terms of using the data of our neighbors. And so I fit a smoother through those individual level slopes. Rather than trying to categorize them into 6 categories, let's think about them as continuous. And you get a very similar type of picture, which is in the middle, you got kind of no association going on. You do have influence from individuals with very high baseline viral loads. And over here, to some degree, you have higher slopes among individuals that have very low baseline viral loads. Okay? But for the most part, in the centroid of that data, there's not a ton going on there. Some influence that's happening over here. Now, if you were to draw a straight line to this, though, with the influence of those things, which is ultimately what we're going to likely be assessing, right, which is that marginal effect across baseline viral load, then you can see that there's a little bit of a negative slope there, right? I don't think I'm... But again, lots of it is based upon what's going on this house here. Okay. So now, again, if you hadn't taken this course, you didn't know much about correlated data, something that you could do to analyze these data, which would be perfectly legitimate, would be to say, I will take my individual level slope estimates. Now they are a univariate response for each person, and I will regress that upon their log baseline viral load. That answers the scientific question, actually. Okay? Everybody agree with that? I mean, that is my first order trajectory change. That's my best estimate of it for each person. It's an induced summary measure, and then I'm just looking to see whether that is changing relative to log baseline viral load. Right? Okay. Again, what are the issues with doing that? I'm saying that it addresses the scientific question, which it absolutely does. This is absolutely a legitimate analysis to do. You've got univariate responses, independent data, perfectly fine. It's a linear regression model. What are the downsides of doing such a thing?
Different numbers of observations for each subject.
Right, so it goes back to what we were talking about yesterday, right, Arnie? So it's the idea that we've got differential amounts of information on each person. In other words, these beta 1 hats were not all created equally, so to speak. Some of them are based upon 9 measurements, some of them are based upon 2 measurements. Yeah, well, no, actually that's not true. Some of them are based upon 3 measurements. I think I got all the ones with 2 measurements. But there's high variation there. And so what that means is that from an efficiency standpoint, it probably wouldn't be such a good idea to weight the slope estimates for individuals that have 9 measurements the same as I'm weighting those individuals that have 3 measurements. You guys with me on that? And so really what we're doing with the general linear model and doing the weighting by the variance covariance matrix is taking that into account. You're taking into account the dependence within a subject in terms of how many observations that they have. and then using that to your advantage in terms of a quote-unquote optimal weighting scheme. That's where the efficiency is coming from. If I were to use an independence weighting correlation structure on my multivariate response data, before I get into the results here, then how am I treating subjects in terms of weight? This analysis gives each individual, regardless of the number of observations, the same amount of weight. Right? I get a beta 1 hat, and it's just in there, and it gets the same weight. If I were to now take our general linear model and say, I'm going to just ignore the fact that I've got correlation on individuals, I'm going to just do OLS, basically an independence working correlation structure, then how am I weighting individuals? I'm weighting them exactly relative to the number of measurements that they have now, right? So now I'm saying the person that has 9 measurements gets 3 times the weight of the person that has 3 measurements. Now, does that make sense? Not necessarily, right? Because those 9 measurements aren't all independent. It's not like I sampled 9 different people and saw them over time. There's a correlation that's going on there. We've seen it already. So they're not independent units. And so the amount of information that I'm gaining on that individual isn't the same relative to the 3 measurements. In other words, as I keep adding on more and more measurements, think about taking 90 measurements or 900 measurements on that person. Are you gaining that much more information on the population? No, you're not, right? I mean, so intuitively you can think about it that way. So that's why you're weighting the correlation structure, estimating it, using it as a weight to give, if you will, partial weight to those additional observations. And the definition of partial comes from how highly correlated they are. If the correlation is 1 between all those observations, are you gaining any additional information? No, right, Francis? I mean, I'm not measuring the same thing over and over again. I'm not learning anything new about the process. Okay, so for this particular kind of simplified analysis, though, if I just regress my estimated beta 1 hats, you can see a couple of things here. You can see, okay, here's our estimate of log baseline viral load. We talked about interpretations here. You'd have to do that really on the multiplicative scale. You want it on the viral load scale, right? Because I've log transformed it. But you can see that it's a similar story from what we had before in the sense that there's a negative slope that's sitting there. That's kind of what you saw in this picture, right? And there's that negative 0.6 that's basically running down there as I'm floating through. And it's kind of, for lack of any better term, I mean, there's reasonable precision on that estimate to say that it's slightly, close to 0, but not, or sorry, slightly away from 0, but not quite. So trying to stay away from the term marginally significant, which I actually hate. So let's do something slightly more fancy again. So that model there says I will give each sampling unit the same weight. Almost the antithesis of that, again, would be an independence working correlation structure. That's what I'm going to fit next. I'm going to jump over into R to do it. So now I'm going to pull in the library GEE that's going to allow me to fit these general linear models in this case, because we're still talking about a identity link here. So just go ahead and read that guy in. Really quickly, let me just point out a couple of things about GEE. If you pull up the help file for it, let me just note a few things here. A lot of it looks similar to what you guys have dealt with in the past. In other words, it's a regression model in R. That means how we parameterize that regression model from the systematic component is through the formula statement, just like we've always dealt with. You do have this ID variable, though, that needs to be there. There is no default on that. The reason why is because GEE is designed and set up for clustered data. So ID is telling you what the cluster levels are. Okay, in our case, it truly is a patient ID. It might be a classroom number, it might be an individual's last name if it's families that you're sampling, whatever the case may be, but this is the clustering identifier here, okay? Data we know, subset we know, NA.action. The major things that we're going to start to deal with now, though, are this guy, right? So you see something called core structure, that's the correlation structure, and you can see that it defaults to independence. And then you see something also that says family over here, and it defaults to Gaussian, very similar to what we had in the GLN setting, okay? So now if I start thinking family is Gaussian for my probability distribution, first of all, when you think family Gaussian from back in our GLM days, what would that imply about a link function for the systematic component? It's identity, right? And so it's just a linear model. And so that's what's going to come through here as the default link. And now I have correlation structure as independence. So if I were to just call GEE with the formula statement and an ID here and leave everything out, what am I doing? OLS, right? It's the same thing as if I called LN and didn't deal with anything else. Okay? All right. And so what we're going to do, though, is going to build upon this. And let me just highlight one more thing here, and that is this correlation structure. As you come down, you will see very familiar names to what we had before. So independence. That's the OLS model that's sitting there. Fixed means that you're actually going to specify what it is. So you're going to feed it in, and it's going to stay fixed. It's not going to re-estimate it based upon the residuals from the model after each iteration. I'll talk in a minute about stationary independent and non-stationary independence. Give me a little bit of time on those. But exchangeable is that random intercept structure that we've been talking about. So again, the same name for that would be compound symmetric. People use those words interchangeably. ARM is just, if you put in an ARM, it's going to assume an AR1 structure. In other words, that row to T, okay, as you're going through a row to the 1. And then finally, we talked about this before as well, the unstructured variance covariance matrix, which says you're going to estimate all those parameters on the off diagonals. Okay. And again, what are the only times it makes sense to start entertaining an unstructured variance covariance matrix?
When you have more observations per person?
Careful. If I've got a lot of observations per cluster, that means sigma is getting very, very big, and I'm estimating lots of parameters with that unstructured covariance matrix. So I think what you want is the opposite of your statement.
Oh.
So
But we need more patience, though.
there we go.
Yeah. Okay.
So when it makes sense to start entertaining an unstructured variance covariance structure, really a few things have to hold. You want lots of independent sampling units. In this case, it would be people in our max data set. Okay? You want relatively few number of measurements per person, in that case, or sampling unit. Bring down the dimension of that. But also, what else? Complete and balanced, exactly. Complete and balanced data. So in other words, you have equal amounts of information to estimate all those parameters as you're going through, right? I mean, if you remember my example for the max data on the very first day before I kind of truncated it down, there were individuals where we only had like 8 or 9 measurements on a particular, like 9 months out. That's not going to work very well for us here. Okay. So those are the cases where you might start entertaining an unstructured variance covariance matrix, but other than that, don't start thinking too much about it. And again, I'll talk a little bit more about stationary independent and non-stationary independent correlation structures later. I'll hold those off. So the final thing I will note about this is there's always something like a tolerance and a maximum iteration, even when you're dealing with family equal Gaussian, as long as it's not in the independence or fixed case. And that's because what's happening is you're doing an iterative process. You're going through, you're estimating beta hat. We wrote this down. From that, you're getting your residuals from the model. You're using those residuals to estimate sigma. You're plotting that, plugging that sigma back in as a weight, its inverse, and then going through and doing an iterative process. So that's what this max iterations is really doing in those cases. So I'll highlight that in just a few minutes here. Okay.
So that's the number of iterations that Newton-Raphson.
It's not really Newton-Raphson, okay, because it's not, I mean, that's not what it's doing. I mean, it does equate to Newton-Raphson in the normal case where you've got a pre-specified variance covariance matrix, but I really just want you to think about it as iteratively weighted least squares until this thing drops down, because there's really not a theory that tells me it's a Newton-Raphson based upon maximizing a log likelihood anymore. It's really just this case. Okay. Yeah, but that is the number of iterations that it'll go through, and then it'll just pop out. Okay. Okay. And you can see that most of these models, just by seeing a max iteration of 25, by the way, are fairly stable. I mean, for the most things that you would fit. In other words, they break down pretty quickly, and you'll see that in just a minute. Okay. So, let me get this where you guys can actually read Okay. So the first model I'm going to fit again, this is almost the antithesis of the simple univariate model that I had before. Now I'm going to give equal weight to each individual observation, not clusters. So that's the independence model here. And so a few things on the response that you're going to see. It's going to come out saying, look, you're doing GEE for dependent data now. Didn't put anything else in, so now I've got that the mean variance relationship is Gaussian. You start seeing where I use, so you hadn't seen all this terminology before other than in my notes, right? Like GLM and those things didn't use that terminology, but like I've been building you guys up since the beginning of 211. When we talk about, when I say things like a mean variance relationship, that's what we call this stuff, right? I mean, you're specifying the second moment as you're going through. Here, when I say a mean variance relationship is Gaussian, what is the implication of that?
There's no mean variance.
It means there is no mean variance relationship, right? Okay. And so now my correlation structure, again, is assumed to be independence in this case, and that's because I've stuck it in down here. That, again, would have been the default to it. Scientific question, this is what we talked about last time. So month, that's time. So that's the underlying slope. So this would be the coefficient associated with month. Again, we talked about this last time, would be the marginal slope across the population of CD4 in a subpopulation of individuals that have viral load at baseline equal to 1, which there are no individuals there, so it's not really that interpretable in this case. But the real scientific question comes down to saying, is this interaction existing? In other words, is the trajectory of CD4 changing depending upon the baseline viral load? Okay. Couple of things before I get to the parameter estimates, because we're used to those. You can see down here, it says something called the working correlation structure. Again, the terminology means something. The reason why we call it the working correlation structure is because folks that are fitting these models really don't believe that they've fully specified the absolutely correct variance covariance structure. It's something that you're working through to basically get estimates. And at the end of the day, once you have those estimates, now you start to see something that comes out just in a summary statement automatically for you. And that is the robust Z and the robust variance estimator, right? It's coming through there. And I have to admit, I really like the terminology. Right? I mean, that's the underlying premise. Is like you're being naive if you think you fully specified this 9 by 9 variance covariance matrix absolutely correctly. Okay. So here, again, this is scientific question of interest here. And then what I would most likely do if I were doing this analysis for somebody is I would be thinking about k-fold increases and interpreting that relative to differences in slopes across those different categories. Okay, I'm not going to go through that. I kind of wrote it on the board last time for you guys in a simple way. You do see something else going on though. There's a slight change in some of these things in terms of the naive standard error estimates versus the robust standard error estimates, as you can see here. And in most cases, for these guys, you see that the robust variance estimate is larger relative to the naive, and that's because the naive is not taking into account any correlation between these observations. So far, so good? Okay. So now let's go ahead and fit the compound symmetric, which is, again, equivalent to saying I'm just going to fit a random intercept model. Okay? So it's exactly the equivalence here. It's the same variance covariance structure. And so now with the random intercept model, the estimation is slightly different than the mixed effects model that I'll talk about later for that, by the way, but it's the same variance covariance structure that you can put in. So a couple of things now that you will see is, one is this thing had to iterate through, so it iterated 3 times, estimating those residuals and then estimating the covariance between all pairwise observations. And you can see something else here. So the common estimate of the correlation between any 2 observations now being held to 0.66. That's after convergence, as everything has come down. If you take that, it's always good to do kind of sanity checks, right? We did an empirical correlation. Oops, let me do it like this. An empirical correlation matrix earlier. You guys can probably find it easier in the notes than I will. That was the empirical correlation estimates that we had previously in class, right? So what we're estimating right now is about 0.65, which should be about the average of all of these things that you're seeing. Okay, again, it should be fairly intuitive what you're getting back at the end of the day. So you're losing, to some degree, that autoregressive type of structure, that fall off, if you will, on neighboring measurements. But you're getting kind of an average estimate here for the working correlation. Okay. So now let's go back up to this guy. You see a couple of things again, naive and robust are always going to be there. This is basically the Huber-White sandwich estimator that's coming back at the end of the day with the empirical variances. And again, you can see things like, okay, now if you start comparing the naive Z's and the robust Z's, there's a big fix there. And that's because you're giving a lot more correlation out here than is probably actually realistically there, and a lot less in terms of those neighboring intervals that are there in terms of the weights. Okay, and so we know that there's some autocorrelation going on, so there's some pretty big changes in terms of these standard error estimates that are there. So the last one, and the one that I would actually be fitting, I'm doing most of these for just pedagogical reasons to show you how you could fit them, but given that we had seen the serial process going through, I would be likely fitting something that would be serial in nature, and so I'd fit an AR1 type of process. And if you do that, first of all, notice how I specified it, and that is by saying, okay, the correlation structure is ARM. The M that I'm specifying here is 1. So you could do an AR2 process for every 2 observations, 2 units across, 3 units across, etc. Okay. So for that AR1 prime process, then you see there's quite a bit of there's not as much variation, I would say, in the naive robust variance estimate, or the naive standard error estimator, and then the robust variance estimator. And that's because you're kind of getting closer and closer to the true variance covariance matrix. Okay, with that simplifying assumption. Okay. Good. Now, a couple of things to note here is that if you look at that point estimate now, it's going to differ from, so that was the compound symmetric to the, say, the AR1. They're going to be different, right? That's because these over here are ad hoc fixes, but what I've got here for my point estimates are using that weight as I go through. So as I change that weight matrix, I'm going to get a different point estimate. Are they all consistent? Yeah. Yeah. Okay. In the absence of missing data, you guys are learning some things about missing data on homework right now. But, now, if I go back up here with the independence, again, I see something that's relatively similar to each one of those as I'm going through. So that's what you would expect. You wouldn't expect to see huge differences in the point estimates across these different models. Now, they will be different, but you wouldn't expect to see huge differences, at least with complete data. Okay. And certainly not if you had a roughly balanced design. Okay. So one of the things I do want you guys, some of us have been kind of trained, I don't know if it's like a Pavlovian response or whatever, is to say I'll go ahead and fit, again, weight matrices until I see a Z statistic that is less than minus 1.96 there. That's not the principle here, okay? All of these, I would say that there is some evidence that says as log viral load increases, there tends to be a slighter decrease in the trajectory of CD4 counts. That would be my take-home statement on this analysis. Whether it was a Z of minus 2.18 or a Z of minus 1.78, that would not be changing my scientific kind of belief in what's happening here based upon my empirical assessment of what's going on, okay? They're all kind of sitting around what people would call marginal evidence for suggesting that there is this. And again, the purpose of the descriptive statistic says it's really not happening around the primary range of where baseline log viral load counts are. Where is the influence coming from? It's individuals that have really high log baseline viral loads or really low log baseline viral loads, okay? So one of the things you might do, sorry, I'll answer your question then I'll answer.
Where did you get that from, that the influence is coming from?
The high and low?
Yeah.
Let me go back.
Oh.
You can see it there.
Okay.
Okay. I mean, you can start to see these people taper off down here as they start getting super high on the viral loads, and then on the other side up over here. You can also see it there, okay, as I divide these guys up. So if I were doing this for a purely descriptive purpose, then I might refit another model that shows the categorical log baseline viral loads as well and shows what the slopes were using the weighted GE model. Okay. So far so good? Yeah? Feel comfortable doing this? Okay. All right. Very good, very good.
Oh, another question.
Yeah.
So, unless the empirical data, empirical correlation suggests otherwise, you always want to use ARM?
Oh, no, I wouldn't say that. No, not at all, in fact. I wouldn't say that. So I would base everything upon the empirical EDA. That's why I was doing the empirical EDA. And the empirical EDA was telling me that there was some serial process that was going on, right? I saw it in the correlation structure, I saw it in the variogram, I saw it all the way through. So, but if I saw something that looked more flat on that variogram, in other words, just kind of this exchangeable process, I would just be using exchangeable correlation structure. Now you do have individuals in the world that actually advocate just always using an independence working correlation structure and just using a robust variance estimator. And I don't quite go to that. There are some reasons that people do that. I don't necessarily agree with them, but the reasons is because you can start to get into nonlinear models, which we will go on to later. You can start to get into some funny things with the weight matrix and consistencies, but it's a much smaller problem, I would argue, than people tend to. Those individuals that kind of report that really need to be worrying about it. So just worried about. So, anyways, most of the time though, I'm doing something simplified though, like an exchangeable or an AR1 type process on these things. And again, that's part of the reason I'm having you guys do that third homework assignment, is to show you just how much you can recoup back on the efficiency. I mean, if that's your goal, is to gain back efficiency, you can gain it back by being just approximate, right? I mean, the exchangeable is basically going to say, I'm just going to average over all of them. And I'll just take an average across these things and wait. Good. Other questions? Yeah.
How do you choose M?
How to choose M. So you can choose M by doing, I'm going to show you guys, actually, can I hold off on that for just a little bit? Because I'm going to talk about it a lot more when I get to mixed effects models, where we do these ACF plots, basically, and we look at autocorrelation functions. And that's going to tell you how quickly things taper off. So let me just hold off just a little bit on that. Okay? Because I'm going to show actual diagnostics to be able to come back to it rather than wave my hand here. Okay. Good. Other questions? All right, everybody should have lecture 9. So now we're going to leave this land of weighted least squares. Again, quote unquote, the general linear model, and we're going to go to a full likelihood setting, okay, so a fully parametric model. If anybody needs a lecture 9, I have a couple extras. Okay. So again, we've been talking about these GEE models. The characterization there, is that you are not doing, we hadn't been doing maximum likelihood at any point in time. Okay, I mean, the idea here was we just started with weighted least squares. And then for the weights, we always used moment-based estimators. Right, there was no kind of maximizing of a log likelihood for any of those variance components. We just took the residuals, slammed them back together, and said, look, if they have mean 0, I can get a moment-based estimate of the variances. Okay? So that's going to be the big distinction between that and what I'm going to now, which is what people would refer to as linear mixed models or linear mixed effects models, which are going to come at this from a parametric likelihood perspective. Okay? Write down a likelihood model, and then maximize that likelihood to solve parameter estimates, both mean model parameter estimates, coefficients, and variance components. Okay? All right. So this kind of dates back to around 82. Laird and Ware were kind of the first ones to propose such a model. And we've talked about it a little bit already, but I'm going to go into much more detail into it now. So the classic, quote-unquote, linear mixed effects model says, hey, I've got a response yi for the ith cluster or sampling unit. I've got fixed effects here and a fixed effects design matrix, xi times beta. Again, this is generally what we're using to answer our scientific question as we've dealt with before. But then I've got also an individual level random effect that's there, okay? And I've got a design matrix that goes with that random effect. So, for example, that design matrix could be just a column of ones, in which case we're talking about a random intercept model. It could be a column of ones and a column of time, in which case we're talking about a random intercept and random slope model, right? And then in that case, the dimension of bi would be a 2 by 1, okay? And then finally, I have this vector of error terms that sits off after I've conditioned upon each individual's random effect. Okay, that we've gone through. And so the typical assumption when somebody in the literature says, I fit a linear mixed effects model, what they are telling you is, I assumed that my random effects are normally distributed, they have mean zero, they have some variance covariance matrix D. It's implicit in that when you say that. Okay? And then that epsilon I is normally distributed, mean zero, and some variance covariance matrix I'll call Ri. And again, the Ri now, notice that the I depends upon the ith individual. The D is common across individuals. Okay? Okay. The other assumption that is typically made is that the random effect and the error term are independent of one another. In other words, once I've conditioned upon the random effect, these things are become independent. Okay? So that gives us then a multivariate normal model. You can see that we're going to start thinking likelihood-based inference here of the form yi xi beta plus this thing I'm calling zi. So I've got this model sitting here. And so my zi is equal to zi bi plus epsilon I. And if you think about what the variance now is for our response, the variance of zi, take the variance of these guys, it's going to be a zi, capital D, zi transpose, plus, and then assuming independence between these two things, an Ri. Okay? You guys with me on that? So that is defined now a correlation structure or a variance covariance structure equivalently for our responses. Okay. Good. So again, as you're thinking about the model, you can think about all regression models in this way, right? You've got a mean response that's a function of covariance, a systematic component, if you will, and then you've got some systematic variation around that mean trajectory. And so the systematic variation in the mixed effects model does something, it's the classic statistics trick, which is to say, I've got total variation and I want to decompose it, right? I mean, that's what we've done since ANOVA back in the 1900s, okay? So now you would think about decomposing that total variation then into the random effects component. That's, again, the variation from a subject-to-subject trajectory that's random then between the subject variation, or random between subject variation across clusters. And then within subject variation, this is the thing I'm referring to as Ri. So that's variation of the individual over time, say, once you condition upon their random effect. Okay. So one of the most popular models then, if you're thinking about modeling slopes over time, is to think about a random intercept and random slope type model. So this would be that particular form, right? So now I've got a random intercept that's sitting here, plus some v1i tij for a random slope on individuals. So what this model is doing, I mean, the easiest way to explain it to somebody is thinking about, okay, across the population I have this marginal first order trend in my response. And then what I'm doing, what my model is allowing for is each individual to have an individual level deviation from that first order trend. Okay? So the magnitude then of the heterogeneity in the population in those random effects, or those random trajectories, if you will, is going to be characterized by that capital D matrix. In this case, it's going to be a 2 by 2, since my random effect vector has length 2. Okay? So how do we now interpret that capital D? It's pretty easy, actually. You can think about root D11. Well, that's just the typical subject-to-subject deviation in the overall level of the response. That's your random intercept, right? How much are people changing across the response? Root D22 is that typical subject-to-subject deviation in the slope across individuals. So that's pretty easy for us to think about. D12, that's the covariance between the individual intercept and the individual slope. And we talked about this a little bit before. I mentioned an example where you'd say you might consider situations where people that tend to start off high, oftentimes what we see is they regress to the mean very quickly. So high intercept corresponds to a low slope, in which case you have a negative covariance between those two things, right? And so you can also think about situations where maybe high also leads to a higher trajectory. If you're thinking about kind of maybe baseline reading levels for kids, oftentimes, kids that come in high, they often, at least early on, progress really fast. Things start to average out over time, you know, in general, but very early on they will progress really fast. That would be a positive correlation between the random intercept and the random slope. That would be a positive covariance between those two things. Okay? So I will argue that there are two primary reasons why at least I myself go to a linear mixed effects model setting versus, say, a GEE type setting that I've been talking about before. The reason, if I'm purely only interested in estimating these marginal terms, I'm kind of GEE all the way because I've got the robust variance estimator to back me up and all those things. But if I have interest, if I have scientific interest in, say, the random intercepts and random slopes, right, Alex? So Alex is doing a project where that is her target of inference, is the random effect, right? She wants to know how people are varying. In her particular case, it's how drivers in NASCAR are varying with respect to their abilities. There, she's really interested in these D11, D12, D22 components that are sitting there. So now you've got to parameterize those things and estimate them. They are of scientific interest. That's one reason. The other reason that I would often go to a mixed effects model case is if I want a predictive model. And if I want a predictive model, I need to borrow off of some probability distribution at the end of the day. In this case, I've got a normal probability distribution, right? Everybody see why I say I need a probability distribution to borrow off of for a predictive model? If you think about predicting a new response and you want to do inference on that, you have to say, what is the distribution that you're pulling that new response from? Right? I mean, you guys did this way back in 2010 when you did prediction intervals, right? You built a linear regression model, and then for a prediction interval, you had like MSE times 1 plus X transpose X inverse for your variance in the homoscedastic case. So what were you assuming there about that new response that you were pulling from? It was coming from a normal, it had the same variance, sigma squared, right? And then you had homoscedasticity throughout your data, right? And it was independent. Okay? That's exactly where that came from. Okay? The GEE model, if you think about it, not going to be very good for prediction. It's going to give everybody the same marginal mean prediction no matter what. Okay? This is going to allow you to estimate those within subject effects. Okay. Or subject-specific trajectories, I should say. Okay. So the other thing that 99 out of 100 times when you're reading the literature and somebody says, look, I fit a random intercept model, or I fit a random intercept, random slope, linear mixed effects model, the implicit assumption there usually is that they are then assuming that this RI, this error term, has variance covariance sigma squared times the identity. Okay. That's what software will default to. That's what most people actually default to be quite honest with you. So what this is saying, and I think it was Arsini that brought it up a while back, this is really saying that if I condition upon my random effect, then I'm assuming all my measurements, then my errors basically are totally independent, conditional upon that random effect. In other words, I've captured everything about the cluster that makes them the cluster, and everything else just looks like random noise. Okay? All right. So That's kind of the most common assumption I would argue that people will utilize in the literature. It's not the only assumption, though, that you could utilize. You could utilize, for example, an autoregressive process like we've been dealing with. So now conditional upon my random trajectory, maybe I still think I have residual autocorrelation. In other words, measurements or errors, I should say, that are taken close together are more highly correlated than errors that are taken far apart. That's not an unreasonable assumption, actually. Because usually you would be thinking that you have residual correlation even after you've conditioned upon one or two random effects. In other words, that doesn't define everything about the cluster that makes them more similar to themselves. Okay? So you might think about an autoregressive structure. You guys have already seen this, where you have these residuals conditional upon the random effect having this autoregressive process or exponential decay process. And this is why I was postponing your questions, so I'm going to come back into it a little bit here. So examples might be, again, a first order autoregressive process that's sitting here. And so you guys have actually seen this already. Now the difference is, before, when we estimated rho, we did it just based upon moment estimates from the residuals. If you're going to do it in a mixed effects model setting, you're actually going to write down the likelihood and try and estimate this parameter if there be a maximum likelihood. The likelihood of stemming from the multivariate normal in this case. Okay. Again, we use the same terminology, which is nice. So we also have the continuous autoregressive process, which just says that time may be staggered between any two observations. And then finally, where most of us will tend to go, to be honest with you, most people that don't know much about mixed effects modeling and longitudinal modeling will just stop right here. They'll just simply say, I put in my random effects, I've accounted for any kind of variation, and they'll just leave it at independence. But people that kind of know what they're doing think, well, there might be this Diggle model again, right? It comes right back to haunt us again. It's the same thing. I mean, we haven't changed, just the way that we're going to estimate these parameters is going to be changing. Where I've got a random intercept that says people tend to be high or low within the cluster, but then I allow for a serial process to come in as well that says, even conditional upon that random effect, I might have observations in time that are closer, having a higher correlation, and then also having a measurement error, right? That says as I start bringing in two observations, there's still some residual error that I'm not picking up in the model that may be instrument-based or what have you, okay? So this is exactly the model that we looked at before. Now we're actually going to parameterize this full model and do everything via likelihood, maximum likelihood. Okay, so I've given you guys already examples on these things of what the random intercept would mean. Like, for example, in the CD4 setting, that would mean some individuals, their normal or steady state for CD4 counts tends to be high or low. That serial process, you can think about that. People tend to think about this as a trait, right? That's where I just tend to be high or I tend to be low. It's a trait of me. And then we think about the serial variation as really a state. So in other words, as I go through time, for example, with the CD4, I might get an infection. And that's going to drive my CD4 levels. Okay? Or I might be immune suppressed because I'm taking medications, and that's going to drive my CD4 levels. So that would be a state that I'm in. And then you would think about measurement error. Again, in the CD4 case, it's a blood sample, so you're doing sampling already. There's lab processing that's going to go on that's going to create measurement error, etc. And we saw that there was pretty good evidence of measurement error, random intercepts, and serial variation in the CD4 study. Okay, so now I'll set the stage for where we're going to go next time, and that is going to be likelihood estimation, right? So what we've got two things that we've got to estimate now. We've got to estimate the regression parameters in the model, our betas, and then the things that are driving the variance components. So I'm calling that alpha. Okay, so if you imagine, what I mean by alpha is if I'm assuming just an autoregressive process, that's going to involve rho, and then say I'm assuming, random intercepts and slopes, that's going to involve D11, D12, and D22. Okay, so alpha would be like all four of those parameters. That's what I'm referring to there. So what we're going to do next time is we're going to say, all right, I've now got a variance covariance structure that's the sigma that's parameterized by this finite vector alpha. We're going to write down the likelihood. That looks very familiar to us. It's just this big multivariate normal. And we're going to do the estimation coming through. Now the trick here is that when you guys did maximum likelihood estimation in the normal model for independent data, what was your estimate for the maximum likelihood estimate for the MSE, for the variance term, the sigma squared, in the homoscedastic case, take you guys all the way back to 210?
Square error divided by n.
As sums of squared errors divided by n, right? And that's what the MLE was. But is that what you used in practice?
No.
No. You use sigma squared, or you use the sums of squared errors divided by n minus p. Why?
It's unbiased.
Because it's unbiased. Because of the fact that you put constraints on that model and you had to estimate the betas to get the means that are going up in that sums of squared errors, right? That same thing is going to come back. And so we're going to contain estimates for this, but the MLEs for this guy in general are going to be biased. Okay, and so that's going to give rise to this